Hello everyone, welcome to 5.3 Taylor and Maclaurin series. We begin with Taylor series. If f has a derivative of all orders at x equals a, just understand that, all orders means all derivatives, first derivative, second derivative, third derivative, nth derivative, and so on. If f has all those derivatives at x equals a, then the Taylor series for the function f at a is given to be summation f of nth derivative of a over n factorial times x minus a power n. Can be expanded like this, right? When n is 0, right, it's just f of a, because 0 factorial is 1, okay? And when n is 0, again x minus a power 0 will be 1, so you get back f of a. When n is 2, that was 0. When n is 1, then you get the first derivative. Remember, this n actually indicates the order of derivative. So it's so because we use the prime notation, it looks like a 1, but I meant a prime notation, so f prime of a. If I wanted to write a 1, I have to put parentheses around it, okay, like that, to indicate the derivative. Otherwise, it looks like a square or a power 1. It's not a power 1, it's the derivative. Okay, that's f prime of a times x minus a. When n is 2, you get the second derivative. When n is 3, you get the third derivative, and everything else matches with that. But look at the fourth one. Only up to the third derivative do we use those dashes, or those, those prime notation, the strikes. After that, we use the numbers, because you just can't go on forever marking those dashes. So you have the fourth derivative written with parentheses. Please do not skip that part, because if you don't use the parentheses, it would mean the fourth power. And anyway, that's how you expand this. And what we say is, this is centered at a, right? The series is centered at a. If your series was centered at 0, then we call it as the Maclaurin series. The Taylor series becomes Maclaurin series when you have x equals 0. Okay. I must say, did I say x equals 0? Sorry, when a equals 0. Okay. When well, you can say x equals 0, yes, because x equals a there. Here x equals 0, so it doesn't matter. But I wanted you to see that it was the a that became the 0, so you still have the x. Okay. Is there a way to prove this? I mean, we can prove this because we saw power series. We also saw the ability to derive when you're able to represent it as a function. So, so we can kind of show the derivation for this by choosing different derivatives. So I'll work on that now. So I'll say proof. So we begin with a function that has a power series representation at x equals a. So we know that if you had, you began with that assumption, then you know that if you wrote your series as Cn x minus a power n, it expands like this, right? C0 plus C1 times x minus a plus C2 times x minus a the whole squared, and so on. When x is a, this series that you began with just reduces to a C0, because wherever you have x, if you plug in a minus a will be 0 for all the other terms, right? And if it's C0, that's the same as f of a, because you're trying to match it with the first term, right? The first term was f of a when you expanded this. So we're trying to use that notation there. All right, take the first derivative of this series. the first derivative of c0 plus c1 times x minus a. This comes out to be 0 for the first one because there is no x there, derivative is 0, plus c1 plus c1 because there's just an x, so I'll just write c1. For the next one, that you bring the power down, you need the power rule, so 2 times c2 times x minus a. Then the next one would be 3 times c3 x minus a whole squared. You will use the chain rule, but here it's times 1, so no changes there. That'll be, the next one will be 4c4 x minus a the whole cubed, and so on. We begin to see the pattern. Right? Now in your first derivative, this is your first derivative, right? In your first derivative, when x equals a, see what you get. When x equals a, the first derivative for cn x minus a power n will be simply c1, right? Because that is your, that's the only term without an x, because everywhere you have an x, you plug in a, they all become 0. So we're going to call this as your first derivative, f prime of a. First derivative of x, right? And x here is a. Okay. Then do the second derivative. For which you have to go back to the first derivative and take it from there. Just to show you that I worked on every step. It's 0 plus 0 for the c1, right? You take the derivative of c1, that's a 0, plus 2c2, okay. Plus, you're taking the derivative here, so the 2, the power 2 comes down, 3 times 2 is 6, 6c3 times x minus a, because the power now there is 1, plus this 3 comes down, so 4 times 3 is 12, c4 x minus a whole squared, and so on. Once again, when x is a, because if you go back to the definition, let me take you back here. It says f has a derivative of all orders at x equals a. That's the reason why we take the order, take the derivative, and then see what happens at x equals a. So the second derivative comes out as 2c2. So this is your second derivative at a. Let's go to the third derivative. For which you go to the second derivative and derive that one. So again, for emphasis, I put the zeros, so you know I didn't skip them. 0, 0, plus that is also a 0. 2c2, when you take the derivative, that's going to be a 0, plus 6c3, plus 12 times 2 is 24c4 x minus a, and so on. At x equals a, the third derivative reduces to 6c3, which is your third derivative. Okay, so you begin to see the pattern now, right? For the fourth derivative, you would have 24c4. You can already see that term here, right? So I'll just say likewise, d4 over dx power 4 at x equals a would be 24c4, which we would call as the fourth derivative of a, right? And so on. So those 3 dots to say that we go on like that. Let's just explore what we have at hand. Okay, f prime of a was c1, so that's good. F double prime of a was 2c2, So if I just wanted the C2, then I have f double prime of A over 2 equals C2. And then f triple prime of A is 6C3. So then if I divide by 6, I get C3. We even did the fourth one, so I'll squeeze that in here. The fourth derivative of A was 24C4. So f fourth derivative of A over 24 will give me C4, and so on. And if you go down to these denominators, you can see that this 2 can be rewritten as 2 factorial, because 2 times 1 would be 2 itself. This can be written as 3 factorial, because 3 times 2 equals 6. This is 4 factorial. 4 times 3 times 2 times 1 is 24. And so on. So you begin to see a pattern. So based on this pattern, you can write a general f nth derivative of in fact, if you look at this one was C1, C2, C3, C4, right? For C4, I had the 4 in the derivative and 4 factorial in the denominator. So if I were to look at it for Cn, Cn would be f of nth derivative of A over n factorial. Agreed? So that's what this means if I were to extend this for some n. Therefore, if I were to put them all together in my series, the series was Cn x minus A power n, right? Now I have a substitution for Cn. So this can be rewritten as n equals 0 to infinity, summation, f of nth derivative of A over n factorial times the x minus A power n. So this the Cn is replaced here. And that is how we have proved the Taylor series. So we call this as the Taylor series. Okay. And we have the uniqueness of Taylor series. Well, the uniqueness says if f has a power series at A that converges to f on some interval A that contains A, then that power series is a Taylor series for f at A. Okay? So that's what this uniqueness of Taylor series says. Okay? If a function f has a power series that converges to f on some open interval A, then that power series is the Taylor series at A. Okay? And if it was at 0, then the Taylor series becomes the Maclaurin series. Right? Now we talk about Taylor polynomials. The Taylor polynomials tell us that if f has n derivatives at x equals a, then the nth Taylor polynomial for f at a is Pn of x, where it's f of a plus f prime of a, that plus f double prime and so on, up to f nth derivative of a over n factorial times x minus a power n. Okay. If you look at the Taylor series, this is the proof. If you look at the Taylor series, it looks very similar to what we just wrote. But then that series goes endlessly, right? Because it goes all the way up to infinity there. But the difference here with the Taylor polynomial is that it is kind of finite. It goes up to n. The nth Taylor polynomial is given to be this. Okay? And these are actually derived from partial sums. Okay? So a quick proof for this would be nth partial sums or sum of Taylor series. That's where this comes from. So if you took P naught of x, right, meaning when your n is 0, you get f of a. P1 of x, you get f of a plus f prime of a times x minus a. You know, that's how partial sums work, right? It's the previous terms sum plus the current sum that you're working on. Then you have P2 of x. Plug in n as 2 for this. So the first term, second term, and the third term would come into this. F of a plus, because the first term was just an f of a, there was no n in it, so there was f of a is going to be there in every term. So you'll always have one more term. So you'll have, for P2, you'll have 3 terms. All right. And if you actually look at this, you can reconsider this as the 0th partial sum. This could be the first partial sum because it's P1. And you could call this as the second partial sum. If you did one more, that would be the third, and so on. Like that, if you have Pn, that will be the nth partial sum, right? The nth partial sum is known as the nth partial sum of a Taylor series is the nth Taylor polynomial. Here comes a problem. Find the Taylor polynomials P0, P1, P2, and P3 for f of x equals ln x at x equals 1. Okay, they want us to use a graphing utility to compare the graph of f with graphs of these partial sums P0, P1, P2, and P3. In our case, I plan to show the picture, an image of the graphs, but it'll be a nice exercise for you to actually go into Desmos and plug them in and test it. Okay, in fact, in the previous lecture I did that, so you could follow the same clue to do it. We did that for a different problem type, but the idea of putting them in Desmos calculator is pretty similar. Okay, so let's start with what is given. F of x is ln x. Okay. So take the first derivative, because for P0, P1, P2, and P3, we will need, at least for P3, we will need the third derivative. So we'll need to go up to the third derivative. This is 1 over x. F double prime of x. Remember that that's x power negative 1. So it's negative 1 x power negative 2, which is negative 1 over x squared. Then f triple prime of x would be negative 1 times negative 2, which is positive 2 times x power negative 3, which is 2 over x cubed. You got this? And on this side, let's find out when x is 1, because that's given in the problem, right? X is 1. ln 1, we know that is 0. F prime of 1, plug in where x is 1, so that's 1. That's negative 1. F1. 2 over 1 cubed, which is 2. Okay, we got all these things. Let's assemble them into our P0 first. P0 of x is f of a. And in our case, a is 1, right? So f of 1, which gave us 0. P1 of x is f of 1 plus f prime of 1 times x minus 1. So that's going to be 0 for that, plus 1 times x minus 1. You simplify all that, you get x minus 1. Okay. P2 of x is f of 1. Remember, it's f of a, but a is 1 here, so I directly plug in 1 for a. That has to be 1. X minus 1 the whole squared. Okay. we know that that simplified to be x minus 1. Negative 1 for f double prime of 1 over 2 factorial. That's x minus 1 minus half times x minus 1 the whole squared. And p3 of x plus the third term so we got the, we'll use p2, which was x minus 1 minus half times x minus 1 the whole square, and focus on the last part. The last part was 2 over 3 factorial is 6, right? X minus 1 whole cubed. So 2 over 6, which becomes 1 over 3. I'll just replace it here, 1 over 3. Alright, so now we'll go to the graph to look at it, to see, we're going to compare, we're going to compare f of x, which is equal to ln x, this, with p0, p1, p2, and p3, where when x is 1. Okay, so we'll focus on 1. So take a look at this. Our p0 was 0, right? So 0 is a horizontal line, so it coincides with your x-axis, as you can see here. And our f of x, first let's start with f of x, because that was our given one, right? F of x is ln x, and you know that's this graph, okay? And then we're comparing p0, p1, p2, and p3. So p0 is a horizontal line, got that. P1, we're trying to find what really works, which approximates better. What you notice is, even for the first derivative, we're focusing on 1, and all these functions are pinching at 1. So at 1, they're pointing to the same value. And that is really interesting, because Taylor series helps us with that. In fact, Taylor polynomial helps us to approximate what happens when x is 1 for the function ln x. And we're using basically polynomials, right? So you have a logarithmic function, but you're using polynomials to approximate its value at a particular point. And so p1 is x minus 1, which is a line. So you can see this blue line here, right? It's a slanted line because the slope is 1. And then if you look at p2, p2 has the square. So the square means you get a quadratic, and that's why this is a quadratic. And you know that the coefficient is a negative half, therefore the quadratic opens downwards. So that's working nicely. And then for p3, the degree is 3, so you know it's going to be chair-shaped. So the red one is a chair-shaped graph. So you can see how the idea of polynomials is displayed beautifully, but then the whole point of what's happening at 1 for the function ln x is beautifully captured, no matter the first polynomial, the second polynomial, the third polynomial. We get them all pinching at the same point, pointing to the same value. Okay. The next question says, find the Maclaurin polynomials p0, p1, p2, p3, and write a formula for nth polynomial. So what we're given here is e power x. Once again, this is not a polynomial, meaning it's not partially a quadratic or a linear function. So you have a polynomial that you're trying to build for e power x. E power x is an exponential function with a natural base e. And so let's test this out. Okay. First, let's write f of x like we did previously and find the derivatives. Because we're going all the way to p3, we need up to the third derivative. What's really cool about e power x is it's the same as the function. The derivative is the same as the function. Derivative of e power x is e power x. And thankfully it was in the simple form, right? If we had e power x squared, then things will change. But this was fine. And they told us Maclaurin polynomials. They didn't tell us what x is equal to. But if you recall, we know that Maclaurin means x is 0, right? Or rather a is 0. I'll just say, because x equals a, we sometimes say x equals 0 or a equals 0. It means the same thing, in the sense that the center is 0. Alright, so f of 0 is e power 0, which is 1. So f prime of 0 is also 1. Okay. Now let's find what p naught of x will be. P naught of x is f of a. Here it's f of 0, which is 1. P1 of x is f of a. Okay, we'll start putting the 0 for a. Which is 1 plus 1 times x, which is 1 plus x. P2 of x okay, P3 of x would be there's one more term here. Oh, cute. Sometimes it gets so monotonous. I forget the factorial or I forget the power, like, you know, I have to be extra careful because I'm creating these videos and it's not like a classroom where I can come back the next day and say, hey, I fixed it. But I have to just be a little more cautious. Okay. Alright, we'll take the P2, so 1 plus x plus half x squared, plus the last term would be 1 over 3 factorial. In fact, I'm beginning to see a pattern. So anyway, let's. I can write this as 6, but I'd like to keep it as 3 factorial because they want us to find the nth polynomial, right? So if we were to go on like this, what will be the expression for Pn of x? So if I'm thinking in terms of the nth polynomial, then I want to see patterns. If I just want to do 1, 2, and 3, P0, P1, P2, and P3, then I will simplify it as much as possible. But here I want to see the so then I look at the P4. P4 would be all of this P3 plus f fourth derivative of 0 will again be 1. So it will be 1 over 4 factorial times x power 4. So instead of writing the 2 as 2 itself, I want to write it as 2 factorial. Okay. So it's like this. 1 factorial x power 1, 1 over 2 factorial x power 2, 1 over 3 factorial x power 3, right? And so that's the pattern we see. We'll put this in a generalized series form. Okay, Pn of x. Now you know that it's a little tricky here now. This is nth polynomial, right? Taylor polynomial. If the nth one, then we go all the way up to n, Pn, right? N terms. So you can't really range your n itself because n, it stops at n. So we want to use a different variable So instead of saying n 0 to infinity, you can't use infinity here because it's finite, it goes up to k. So you can't say n 0 to n, right? That'd be meaningless. So use a different letter and say k goes from 0 to n. And then I will have it as x power k over k factorial, right? Now you keep generating different values for k, you get the previous step. Okay. Here too, if you looked at the graph, you can see what happens at 0. Okay, so we'll take a quick look at that. I have a few graphs here, so let's focus on this one. Okay, e power x, okay, that's this blue one. Okay. E power x is this blue one. So we are interested at 0, okay? And again, as we expected, they all pinch at 0, so it's all good. P0 is 1, so it's a horizontal line at 1. P1 is a linear function, so you see it's an orange line passing through 1 at 0, passing through the y-intercept 1. P2 is a quadratic, right? It's 1 plus x plus half x squared. So it's a quadratic, so you see the parabola. Then P3 is cubic, so you see the cubic function. The red one is a cubic function, and beautifully they all meet at 1 when they pass through the y-axis. And so when x is equal to 0, the Maclaurin series, you get them all happening or meeting at the same point. After that, they go on different ways, right? That is why we keep insisting when x equals 0, or when x equals 1, when x equals a certain a. That information is important because it doesn't work throughout, it works at a particular point of interest. Okay. Let's try for a trig function. So that's going to be f of x equals sine x. Take the derivative. This is again going to be interesting because derivative of sine is cosine, and the derivative of cosine will be negative sine. So the sine, the SIGN, the negative or the positive sign, that will change in front of the function, but it's going to be always fluctuating between sine and cosine, right? We'll go up to 3, so this will be a negative cosine x. And correspondingly, what was this? Maclaurin, right? So yes, it's f of 0. If it's Maclaurin, you know your a is 0, or x is 0 in this case. So f of 0 is sine 0, which is 0. F prime of 0 is cosine 0, which is 1. Negative sine 0, 0. Negative cosine 0 is negative 1. Alright, so we find P0 What is it, P0? No, it was P0 of x, right? Okay. That was f of 0, which is no, f of 0 is 0. P1 of x. Okay. I just want to start plugging in the values, so you know that when I'm doing the P1, I'm using this formula, right? So 0 plus 1 times x, which is simply x. P2 of x, 0 plus x plus 0 over 2 factorial times x minus 0 squared. Okay, I'm skipping the general form and I'm directly plugging it in. So if you want to, you can pause the video, do it, in an expanded form, and then check back here. Okay, so that's going to be x plus x squared over 2 factorial. I apologize, that's going to be, I meant 0 plus x plus 0, because it's 0 times something is 0. This also comes back as x. P3 of x is 0 plus x plus 0 plus, this time it changes, right? Negative 1 over 3 factorial x cubed, which is x minus x cubed over 3 factorial. So we wanted to do only p naught, 1, 2, and 3, but they wanted us to find a general n. So I am not able to see the pattern, because look at this. You get 0 for p. For 0 it's 0. For 1 it is x. For 2 it is x again. For 3 it is x minus x cubed over 3 factorial. So we're not able to see the pattern. So go for more terms. You always want to do that. The p4 of x would be, if you see this fluctuating pattern, it's x plus 0 minus x cubed over 3 factorial plus 0. So p4 will also give back x minus x cubed over 3 factorial. I'm beginning to see a pattern. It looks like they repeat because of the 0, right? The intermittent 0 between two consecutive terms is helping us to see a certain pattern. P1 and P2 come out to be the same. P3 and P4 come out to be the same. So if you want, you can go further and verify what happens. At least to draw the pattern, this will be 0 plus x plus 0 minus x cubed over 3 factorial plus 0. This again should be a minus, isn't it? Because, no. Because you had, yeah, this has to be a plus, because you finish the cycle of the minus, 1, 2, 3, 4. So you go back, so that should be a positive. Positive 1 over 5 factorial x power 5, right? X minus 0 power 5, which is x power 5. So that's going to be x minus x cubed over 3 factorial plus x power 5 over 5 factorial. Okay, that's good. So now we can see the pattern very clearly. First, let me write the pattern as to how I see it. The pattern I see is P1 equals P2, P3 equals P4, and we expect this P5 to be equal to P6, and so on. Now, how do I generalize this? So to generalize this, we're trying to test it, okay? So let's say Pn of x is Pn plus 1 of x, okay, n greater than or equal to 0. We have to change away from n because n is a generalized one, so maybe I'll use the k. Okay. Right, I have to write Pn of x, so I don't want this n and that n to be confusing. So let's test it. When k is 0, P0 will be equal to, P0 will be equal to P1. That is wrong. No, P0 is different. P1 is equal to P2. So come back and tweak it. Okay. What if I added a 1 here and a plus 2? Right? It's always one more than the other one, right? P1, P2, P3, P4. So let's test this. When k is 0, we get P1 equals P2. Very nice. When k is 1, we get 1 plus 1, 2. P2 equals P3. Oh, that is wrong. P2 is not equal to P3. You want to jump to the next one, right? You want to do P1 equals P2, then you want to go to P3. But if you kept this format, it's kind of giving us P2 equals P3, then it will be P3 equals P4, which is desired, but then it will give us P4 equals P5. So you notice that we have to skip that term in between. And whenever you want to skip it, you want to always do it as 2 times. Okay. And if you're doing it 2 times here, you have to fix that 2 times there. That way you keep skipping it. So let's try it now. When k is 0, P1 equals P2. When k is 1, 2 times 1 is 2, so 2 plus 1 is 3. So 3 here, and when k is 1, 2 times 1 is 2 plus 2, 4. So 3 and 4 here. When k is 2, I get 5 and 6. When k is 3, 7 and 8. Okay, perfect. This is working nicely. So we kind of generalized it. So now let's, we also have the changing signs, right? It's alternating series in that sense. So we come back and write the general form, okay? Pn of x, okay? Summation k 0 to n, right? It has to go up to n. Negative 1 power k x power 2 k plus 1 over 2 k plus 1 factorial. And now let's check the graph at 0. So sine x, you know, is a wave pattern. So you got that f of x to be sine x. P1 again was P1 was x, right? Or where's the P0 was 0, by the way, right? P0 was 0, so it's right there at 0. Okay. P1 is a line. P1 was x itself, so it is the diagonal line. P1 is the same as P2 we saw. So P1 and P2 both are x. Then we saw that P3 and P4 are the same, and they came out to be a cubic function. Okay. So you see this, and it was a negative cubic, so you have the direction changing here, right? That's P3, which is the same as P4. Let's see if I can just write that. It's the same as P4 of x. This was the same as P2 of x. And that's P0 of x, which was 0 itself. And P5 is the same as P6 of x. And P5, we extended, right? So we got that as the 5th degree. And so that's the graph of 5th degree. And notice that in all these cases, a point of interest is at 0. This is a Maclaurin series. At 0, they all pinch at the same point. Okay. Now let's talk about Taylor's theorem with remainder. Taylor's theorem with remainder. Remember, remainder is to do with error, finding an error estimate. Let f be a function that can be differentiated n plus 1 times on an interval I containing the real number a. Let Pn be the nth Taylor polynomial of f at a, and let Rn be f of x minus Pn. So Pn is the first n, right, polynomials. So out of the f of x, which goes indefinitely, if you remove the first n, the leftover would be your remainder, right? So this, in particular, if you took away n, that kind of tells you that's the nth remainder. Then for each x in the interval I, there exists a real number c between a and x, such that Rnx, this Rnx can be defined by the n plus 1th derivative. Okay, so f of n plus 1, c, which is the n plus 1th derivative of f, over n plus 1 factorial, times x minus a power n plus 1. Okay. And if there exists a real number such that, and if you have a real number m, okay, capital M, then you have the absolute value of f power n plus 1 of x is less than or equal to m, right? Because it's limiting, so it's always less than or equal to a particular value m, a real number m. And we're saying, well, if we had that condition for all x in the interval, then absolute value of Rn of x is less than or equal to that m times this. Well, you can kind of see the derivative for this one. I'll show that part here. Oh, actually, I could bring it from here. If you could find a number like this, right, what we're saying is, well, go ahead and multiply up and down by n plus 1 factorial if I multiply both sides by n plus 1 factorial and by absolute value of x minus a power n plus 1. What we're saying is this whole thing, let me clear this. The whole thing on the left, you can rewrite that, bring the absolute value, kind of broaden it so that you can bring in all of these things, right? Yeah, because your wherever you have x, that's where the absolute value matters. So the n plus 1 factorial really doesn't need the absolute value, but it doesn't hurt to have it because there's a reason why we want to do this. So we have this on the left, less than or equal to m over n plus 1 factorial x minus a power n plus 1. Okay, and you know that this whole thing in turn is the same as Rn but in absolute value. So then we say Rn is less than or equal to m over n plus 1 factorial, and that is what you see up here in the formula. Right? You can compare these two in the formula. And so that is the way we derive this last statement in the theorem. Let's go ahead and use linear and quadratic approximations to estimate function values. So we consider the function f of x equals the cube root of x. Find the first and second Taylor polynomials for f at x equals 8 and use a graphing utility to compare the polynomials with f near x equals 8. Let's start here. F of x is given to be cube root of x at x equals 8. Okay, that's our focus. So let's rewrite f of x as x power 1 over 3 because we're going to take the derivatives. It's easier for us to keep to this. Okay, f prime of x power negative 2/3 negative 2 over 9, that minus 1 will be negative 5 over 3. Negative 5 over 3. We'll go one more because we don't know if we need it. That's going to be negative 2 over 9 times negative 5 over 3. Okay. So that's going to be 10 over 27. So that's positive 10 over 27. X power minus 1. So that's negative 8 over 3. Yeah. Actually, we just need 2, I think, because we're just doing the first and the second Taylor polynomial. Yes. Okay, no harm. We'll go ahead and find f of 8. Okay. Well, that's cube root of 8, which is 2. F prime of 8. Okay, you can use your calculator to get this, but we'd like to keep it as a fraction just because we want to see the thing, the way it just to look for patterns. But it's totally fine if you want to keep it as a decimal value. The only catch is it won't be a terminating decimal number. So because this, as it is, this is an approximation. We don't want to approximate it too early. Okay. All right. So when you apply this, you get 1 over 12. Okay. Because cube root of 8 is 2. So 2 power negative 2 is 1 over 4. So 1 over 3 times 1 over 4 is 1 over 12. F double prime of 8. negative 8 power, so 2 power 5 would be 32. 32 times 9 over the 2 on the top, that will be 16. So okay, that will be negative 1 over 144. Okay, we don't need this, so I'll just remove this. Because the first and the second Taylor polynomials are required, we will go with P0 or P1 of x. In this case, it's P1 of 8. Therefore, it's f of 8 plus f prime of 8 times x minus 8. 2 plus 1 over 12 times x minus 8. 2 plus x minus 8 over 12. And P2 of x, f of 8 plus f prime of 8 times x minus 8 plus f double prime of 8 over 2 factorial times x minus 8 squared. Right? It's 2 plus x minus 8 over 12 from P1 minus, so negative 1 over 144 times 2, which will be 1 over 288 times x minus 8 squared. Okay, this is sufficient for us to go ahead and graph. So I would like you to use a Desmos. Pause the video when you do this. So take the Desmos, go into Desmos and do your f of x, P1 and P2, and observe near x equals 8. The graph I get, the picture I see here, show you here, is again, notice that your focus is on 8. Oops, bad idea. Okay. And at 8, what happens? They all pinch at the same point. Okay. And this was again not a polynomial function that we started with. We started with cube root. It was a cubic function, right? Polynomial functions don't have fractional powers. So this, we started with a fractional power, a radical or a rational exponent. And so we used the graphing utility to see what happens near 8. They all pinch at 8. Okay. Even the very first two approximations, the first two Taylor polynomials give us a good value there at, good estimate at 8, because they all point to the same value. Okay. So what happens if you were looking at if you're looking to estimate cube root of 11? Okay, can you find an answer? So here we left them as fractions, right? But what if you had a very definitive a value you had to find? So let's say use the two polynomials to estimate cube root of 11. So then I'll say, well, cube root of 11 is approximately your P1 of 11, right? So go back here. So P1 of x, wherever you had I mean, the A was 8, right? The A was 8. So we come back here and say P of, I'm sorry. So you're using cube root of x format. And in this case, your x is 11, where x is 11 and your A is 8. It's the same problem, so we're starting with part B. So x is 11 and A is 8. So you no longer have the x factor to make it to keep it as a variable. Now we have specific value for x. Okay. All right. So I'll just come back here. We'll just use right here. So P1 of x was 2 plus 1 over 12 times x minus 8, right? I'll just write that. And here x is 11, so 2 plus 1 over 12, 11 minus 8. So you get 3 over 12, 4. Because we want an approximate answer, right, a numerical answer, you want to give it as a decimal. In this case, it was fine because it was not a it was a terminating decimal number, so there was no problem in getting the answer in the decimal form. For the second one, if you are using the second polynomial, let's go to the second one. It's 2 plus x minus 8 over 12. 8 minus 1 over, where I'm getting these numbers. Okay, yes, 288 times x minus 8 the whole squared. Once again, your x is 11. So 2 plus 11 minus 8 over 12. 1 over 288, 11 minus 8 squared. Of course, pull out your calculator and evaluate. We get 2.21875. Okay. And what you notice is as you keep increasing it, the nth polynomial, you get a better approximation because you get closer to it. Right? Okay. Then here comes our third part. Using Taylor's theorem to bound the error. Oh, use Taylor's theorem to bound the error. That's all they say. So try to understand what they mean. Well, remember that all this is approximation, right? In fact, with the first polynomial, you got 2.25. The second polynomial, 2.21875. So there is a difference in the values. You didn't get the exact value. So there is some error there, and we're trying to bound that error. Okay. And for that, we use the remainder theorem technically. So we have two things to consider here. You want to look at the Taylor theorem, of course, but also look at the uniqueness theorem. Okay. And so in this case, we have cube root of 11, right? So if you're looking at the interval 8 to 11, for that, let me take you back quickly here. I need to recall what the theorem was. For each, this is the theorem, okay? Taylor's theorem with remainder. Okay, we know Rn is this. Then for each x in the interval I, there exists a real number c between a and x. So for us, it's between 8 and 11, okay? So there exists a c in this interval 8 to 11 such that the remainder, when approximating the cube root of 11, by the first series will give you a certain expression, by the second series, and so on. So I'll take you back here. So I'm calling upon that, and that's how I get this interval. Okay. A to x, A to x. In this interval, there exists, that's a symbol for that, but let me write it here. There exists a c. So if we can find, if we know what c is, that's good. But because we don't know what c is, we need to find an upper bound. Okay, so let's write. Let me complete this. There exists a c such that the remainder when approximating cube root of 11, right, by the first Taylor polynomial, okay, would be R1 of 11, right? It's Rn of x, so it's Rn of x. N here is 1 because we're looking at the first Taylor polynomial. So R1 of 11. Okay. I just want to write it the general form the first time, okay? Because it's too much for me to go back and forth. So Rn of x is given to be f of n plus 1 of c over n plus 1 factorial of x minus a power n plus 1, right? So I'm going to use this one in this case where n is 1 and x is 11. So that's n plus 1, so it is 2, but we don't put the 2, we put 2 strokes, okay? The prime, double prime, of c is unknown to us at this point, over 1 plus 1, so 2 factorial, x is 11, a is 8, 11 minus 8, 1 plus 1, 2. Okay, we plug them all in. Now we know that f double prime of x go back. We don't know about the c, but for x, for a general x, f double prime of x was negative 2 over 9, x power negative 5 over 3. And when x was particularly 8, we got negative 1 over 44. So let's use these two details. F of x, f double prime of x is negative 2 over 9, x power 5 over 3. And f double prime of 8 is negative 1 over 144. So you can kind of see that this could be the upper bound, meaning the largest value of absolute value of f double prime of x, okay, occurs at x equals 8. So you can check the graph for this to understand what happens at the f double prime of x close to 8. So I'll say the maximum value of f double prime on the interval, we know the interval is 8 to 11, is absolute value of f double prime of x, and that occurs at x equals 8. So we use the information that f double prime of 8 is negative 1 over 144, but when you take the absolute value, it becomes positive 1 over 144. And this means we could use absolute value of R1 of 11. This is coming from the theorem, is less than or equal to, you know, that m over, okay, let's write this again in the general form, okay, m over n plus 1 factorial to the value of x minus a power n plus 1 for all x belonging to this interval 8 to 11. And with this, m is actually your it's actually positive 1 over 144 because you take the absolute value. So it comes back as positive. So in the next step, I'm going to plug them all in. R1 of 11, 1 over, okay, I'll just put it, it's 1 over 144 divided by 2 factorial. So, you know, it's going to be positive, so it's x minus, not x, and we now have x as 11. 11 minus 8 power 2. Go ahead and compute this. That gives us R1 of 11 is less than or equal to 0.03125. Okay. And if we wanted to estimate for R2 of 11, we will need the third derivative, so we'll have to go to the third derivative. Okay. So this is for one of them, and I will leave the other one to you. So do the similar pattern, but for R2 of 11, let me just write that part here. Similarly, I'm using all shortcuts here. Similarly, if you did R2 of 11, it will be absolute value of F triple derivative of 8 over 3 factorial 11 minus 8 cubed. And that would be approximately 0.0065104. I'm giving you the answer, but I want you to go back and check this out. Okay? Then we have the one last part. Approximating sine x using Maclaurin polynomial. Previously we saw for sine x, because the derivative brought us back to between sine and cosine, right? When you took the derivative with the opposite signs. And we saw that P1 was equal to P2, P3 was equal to P4, and so on. And we also kind of generalized it like this, right? Where we had all these odd powers lining up. So we're going to keep this as our guide to answer this question. Use the fifth Maclaurin polynomial, because this is the Maclaurin polynomial for sine x. Use the fifth Maclaurin polynomial for sine x to approximate sine pi over 18. Okay. And you need to find and unbound the error. Remember that we are approximating it, so there will be an error that we need to find the bound for. Like in the previous example, the bound was that the error will be kept within 0.03 for the first Taylor polynomial, and it will be within 0.006 for the second Taylor polynomial. And as you can see, the error gets smaller and smaller. The bound is getting really small because the error is minimized as we increase the number of Taylor polynomials. So that is what they're asking us here. They're asking us to find for the fifth one. Okay. So P5 of x would be x minus x cubed over 3 factorial plus x power 5 over 5 factorial. Okay. Using polynomial approximation, we can say that sine pi over 18, okay, can be approximated to the fifth polynomial, because that's our focus here, when x is particularly pi over 18. Right? This P5 of x was for sine x. So if your sine is not x but sine pi over 18, your x is now pi over 18, and you could start replacing all your x's with pi over 18. Use your calculator to compute this. This comes out to be 0.173648. And that is the part where we have approximated it. Now we need to estimate the error. We know that P5 of x is equal to P6 of x, right? We've seen that before. So let's call upon that to calculate. We can use it to calculate a bound on R6, because remember you want the n plus 1, right? Your n here, the focus is 5, so 5 plus 1 is 6. So you're focusing on 6. So R6 pi over 18. That's what you're trying to find the bound for. Okay. So let's write. The remainder r6 pi over 18 is given to be n plus 1, right, in the formula. So that's going to be the seventh derivative of c over 7 factorial pi over 18 power 7 for all c that lies between 0 and pi over 18. But if you go back and recall the derivatives we took for sine, right? I wish we can go back. Okay, let me try to go back. Can't be too far off. Here it is. So if you recall the sine, the derivatives, right, fluctuated between 0, 1 and negative 1, right? So it's 1, 0, negative 1, 0, negative 1, and so on. So this was the third one was negative 1. So the fourth one would be, if you go back to the pattern, the fourth one would be 0. The fifth one would be 1. The sixth would be 0. The seventh would be negative 1, isn't it? Doesn't matter what this is, but you know that for the seventh one is negative 1. And come back here. We are using the seventh, yes, we're using the seventh derivative. Yeah. Now, if you recall, we use the absolute value, right? Absolute value. So this is going to give us the maximum, but this is m will be the maximum value, which is found by taking the absolute value of the seventh derivative of c. And here we, it doesn't matter what the c is. We found that it was going between negative 1 and 1. Those were the two extremes. But when you throw in the absolute value, it can't go, it doesn't matter whether it's negative 1 or 1, it cannot go more than 1, right? The upper bound is 1. This is true for all x, where f7th of x is negative 1. Okay, so we are looking at the upper bound, not the lower bound. So we're looking at the upper bound, and we know that it's not going to exceed the 1 because we saw that it went back and forth between negative 1 and 1. Okay, so let's extend this. Absolute value of r6 of pi over 18 should be less than or equal to over 7 factorial times pi over 18 power 7. Okay. And that comes out to be 9.8 times 10 power negative 10. The error is really, really, really small. Okay. Next, we find the Taylor series to determine the interval of convergence. Okay. This is going back to our power series lesson and connecting that with Taylor series because of the uniqueness theorem. Okay, a power series, if it converges to f, if it's represented by f and it converges to f on an interval I, then it is a Taylor series. So we got that. Find the Taylor series of f of x equals 1 over x at x equals 1. Determine the interval of convergence. F of x is 1 over x at x equals 1. F prime of x is negative 1 over x squared. F double prime of x negative 3 times 2 over x power 4. Trying to build a pattern here, because they want us to find a Taylor series for the function. Okay. So that becomes a positive actually, because it will be a negative 4. So 4 times 3 times 2 over x power 5 and so on. If I were to expand this, this comes out as n times n minus 1 times n minus 2 times 1 over x power, it's 1 more than the this is the same as n factorial over x power n plus 1. Now let's look at the derivative at 1. Okay, f of x. So f of 1 would be 1 itself. F prime of 1 is negative 1. F prime of 2 is negative. No, f prime of 2 will be positive, right? So that's 2 over 1. So I'm trying to build a pattern. So I put the 2. I don't know if the factorial will continue. It seems like that. That's a 1 there. F double prime of 1 is negative 3 times 2. So why not I put it as a factorial? Hold on. This is 2. And this is 3. It's positive 4 factorial. Okay. Because x is 1 in the denominator, it just becomes 1 power 5, 1 power 4, and so on. Okay, so if I were to expand this, the nth derivative of f of 1 comes out to be negative 1 power n times n factorial. Remember, you have to bring in the negative 1 power n because of the opposite signs, the fluctuating signs. This is true for all n greater than or equal to 0. Okay. We got both these patterns. This implies Taylor series for f at x equals 1 we're going back to the definition of Taylor series. So this is what we had, okay? And we saw that the nth derivative of f of 1 actually came out to be this. So summation n 0 to infinity. It just was negative 1 power n factorial over n factorial x minus 1 power n. Right? That's what you have there. So these will go away, leaving us with summation n 0 to infinity negative 1 power n x minus 1 power n. Okay, so we found the series. They asked us to find the Taylor series, right? Find the Taylor series. We found that. Then it says determine the interval of convergence. Okay, so for that we have to go back to the lesson, actually chapter 4 and what we did in 5.1. So interval of convergence requires us to consider this. And first figure out if it converges or diverges, and where it converges, where it diverges. Remember that? It said if it converges at A, then it diverges at all other points other than A. That could be one condition, or it could converge throughout the interval, or it could converge for a radius, okay, for an interval around the center. So we're going to call upon that, but even to establish convergence or divergence, we have to go back to those tests. Yeah, these ones. Remember this one? So it could be any of these tests that we may have to use to handle this. And if you come back to our lesson, yeah, we have the power, right? This power here, you could use a ratio test perhaps, okay, and see what happens. Try any other test if you feel like you think that you have a better test. You can totally try that out. Okay. So for that, the ratio test, I'm just trying to take the ratio of n plus an plus 1 over an. We know you have to do the limit and all that. We'll come to that. Okay. So I'll just write here. Rho is infinity. That's -1 power n plus 1, x minus 1 power n plus 1 over, yeah, and we've seen the simplification many times before. And these go away. And the -1 inside the absolute value bars gets absorbed. So you get back, so you can kind of lose the -1, but we do have absolute value of x minus 1. Okay. So the series will converge if so by the way, there is no n in this formula, right? There's no n here. So this actually comes back as absolute value of x minus 1. Rho is this. If there was n, then we can apply the limit for as n approaches infinity. So this comes back as x minus 1 with the absolute value bars. And we know that rho will be, if rho is less than 1, right? Between 0 and 1, but rho is less than 1. This is absolute value bars. So if it's less than 1, it converges. The series converges, right? So we have to find out for what x this will work, and okay, I'm just trying to show it here. If rho is less than 1, the series converges. Okay. And this implies rho, which is now absolute value of x minus 1, must be less than 1, and use the absolute value inequality rule to split it up like this, and then isolate x in the middle. So 0 less than x less than 2. So you get the interval 0 to 2, right? Now we need to figure out what happens at 0 and at 2. Do we have convergence at 0 to? So that's what we're trying to learn here. Okay. To help us understand this, I want to recall one of our past lessons. Okay. If you recall this convergence of a power series setup, right? This is where I gave you the 3 diagrams and said, well, it can converge this way, this way, this way. And in one of these problems, we had to see the endpoints and see if they converged or not, so that we could use a bracket or a parenthesis based on that. So this is what we're trying to do here. Okay. So let's try what happens at 0 and at 2. Okay. When x is 0, let's see if it converges or diverges. Okay. We know it converges here. When x equals 0, summation n 0 to infinity -1 times power n times x minus 1. So x is 0, so 0 minus 1 power n actually comes out to be negative 1 power n and negative 1 power n. So same thing twice. So we have n plus n, which is 2n. Negative 1 power 2n. Add the powers, right? Now if it's 2n, whatever be n, even if it's odd, when it's multiplied by 2, you'll always get an even power, right? Think of it. If n is 1, 2n will be 2. If n is 5, 2n will be 10. So if the power is always going to be even, there will be no negative 1. There'll be no negative sign resulting from this. So this is going to be summation n 0 to infinity 1 of 1. So that means you're doing 1 plus 1 plus 1 plus 1 plus 1 and so on up to infinity. So do you think it converges? No, this diverges because you have no end to the sum of those ones, right? So this is, it diverges at 0. Okay, it diverges at 0. So we keep an open parenthesis at 0, so we can see that. Next, let's test for the 2. When x is 2, summation n 0 to infinity, negative 1 power n, 2 minus 1 power n. Okay. So that's summation n 0 to infinity, negative 1 power n, and 1 power n. One power n, you know what that is, right? 1 power n is still going to be 1. So it's immaterial to worry about that. So you just have this term dominating, negative 1 power n. And you know that this is definitely going to fluctuate, right? It's going to go between 1 and negative 1 depending on n. When n is 0, this will be 1. When n is 1, this will be negative 1. So it's going to be down and up, down and up, down and up. And so this also diverges. This implies the interval of convergence is 0, 2, open parentheses for both. All right, and this is truly the last part. Okay, I will just define the convergence of Taylor series, and then I will touch a little bit on Maclaurin series, and we'll be done. I know there's a very lengthy lecture. It's tiresome for me as well. Let's finish this off, but this is going to be a full use of our 2-hour lecture. Okay. Convergence of Taylor series. Okay, convergence of Taylor series tells us that if f has derivatives of all orders on an interval I, then summation f of a with the nth derivative over n factorial times x minus a power n, that's your Taylor series, if that converges to f of x for all x in I, that will happen if and only if limit of the remainder Rn of x as n approaches infinity is 0 for all x in that interval. Okay. We'll bear this in mind, and we're going to find Maclaurin series. So we'll be given functions, and we're going to use those functions to find Maclaurin series and its interval of convergence. Okay. So here's the question. Find the Maclaurin series and its interval of convergence use Taylor's theorem with remainder to prove that the Maclaurin series for f converges to f on that interval. Okay, the first one is we're given e power x. In fact, we're only doing one of them, so forget it. It's e power x. Okay, the function given to us is f of x is e power x. Okay. Now, Maclaurin polynomial for e power x, we figured this out earlier, right? So we're going to just call upon that. I'll say using nth Maclaurin polynomial. Remember, Maclaurin is when your a is 0. For e power x, remember we did that. In fact, we did each time we took the derivative, it gave back e power x, right? So it was easy for us to actually build this power series. So we got that. So for the f, the corresponding function the function can be represented for this power series, which is summation x power n over n factorial for the e power x. So e power x is equal to this. Okay, so we got that, but we need to determine the interval of convergence. Okay, you see the factorial, so we have to use the ratio test. Okay, to determine the interval. Again, remember the interval is that interval, right? Meaning you give the values 0 to 2, 8 to 11, -1 to +1. That's the interval. But to even determine that interval, we need to know where this converges or diverges. That's why we go back to those tests. So rho is limit n approaches infinity. I'm going to flip it here just to, that's n plus 1. Okay. Okay, now again the focus is on n, so we can pull out the x. Moreover, x can fluctuate, it can take positive or negative values, but n can only take positive values, so the absolute value remains for the x, and that's pulled out because of the constant nature of it. 1 over n plus 1. And we know that this is going to be, this approaches 0. So x times 0 would be 0. So rho equals 0 is what we get. And this is true for all x. Doesn't matter what the x is, this was true for all x. So the interval of convergence is -infinity to infinity. Okay. So we were asked to find 3 things, right? Find the Maclaurin series and the interval of convergence, and then use the remainder theorem to prove. So we're moving to the third part. Okay. So in order to use the remainder theorem, let's focus on nth derivative of x. That's still going to come back as e of x for all n greater than or equal to 0. This is true, right? That was really neat because we could kind of generalize it very simply for e power x. E power x is an increasing function on this interval, right? It's increasing. So you're looking for an upper bound to bound it, and if you look for that, you see that it goes on increasing, right? Okay, so what will be the maximum value? So to find the maximum value, we use the absolute value of Rn of x. So this has to be less than or equal to m over n plus 1 factorial times absolute value of x power n plus 1. Right? So think about this. What could be that m? Now, the maximum value for e power x, okay, for any, let me write that out here. Maximum value for e power x in a certain interval, in a certain interval like this, right? This interval would be actually negative b less than x less than b. The maximum value for e power x would be that e power b. Does that make sense? Because it keeps on increasing. So if you are limiting it to an interval of negative b to b, you're looking for the maximum value. Because it's increasing, it won't be the negative b, it will be at b, and so it will have to be e power b. So we're using that information to replace the m with e power b. Okay. That's less than or equal to e power b. Absolute value of x power n plus 1. And we also just saw that your let's come over here. So if you took the absolute value of x power n over n factorial, that's what we did here, right? We saw that that converges for all x. We just proved that. So we have that information. So what okay, sorry, I have to go back again here. So if you look at the convergence theorem, it says limit Rn of x if it's equal to 0. Okay, this condition will happen if and only if, right? This condition will happen if you know that the this Taylor series converges to f. So if the Taylor series converges to f, right, that will happen if and only if limit of Rn is equal to 0. So if I show that limit of Rn is equal to 0, right, then I have, proved that the series, in this case, it's not Taylor series, it's a Maclaurin series because it's a special case of Taylor. So we'll prove that the Maclaurin series for f converges to f. Okay. So we'll say Maclaurin series of f converges to if limit of Rn is equal to 0, right? For all x in that interval. Okay. And so that's what we're trying to approach here. So we take limit apply limit on both sides. It's less than or equal to, it's less than or equal to, but we can keep it as it is, or you could use just the equals part because that's what matters, that it's equal to 0. If it's equal to 0, then we have shown that condition to be true. Oh, I have to apply the limit. Okay. E power b is a constant, so that can be pulled out. If we recall divergence test, this goes to 0. Okay, and that's from divergence test. I mean, it was a problem on its own, so we're not going to go over to do that. We just have to call upon this. I know it's a little complicated. How do I remember these things would be your question. Well, that's one of the complexities of this course. However, I'm trying to show you these examples so that you have an idea of how to approach a problem, and if you have to, you'll have to go back to earlier problems where we derived some answers and use them. If not, you would have had to apply that divergence theory test here to get that answer. Okay. Anyway, so based on these, the combination of these give us limit n approaches infinity, absolute value of Rn of x to be equal to 0. Well, we have less than or equal to 0. That's another point. We have less than or equal to 0, but I'm saying that it's equal to 0. We can do that by using squeeze theorem, because what you could do is, we know that this is a divergence test, so you could set up another inequality, right? 0 less than or equal to this, less than or equal to limit absolute value of x power n plus 1. Oops. Yeah, and then we know that this goes to 0, right? I just said that this goes to 0. So if by squeeze theorem, the ends, if this is 0, this end is 0 of the inequality, this end of the inequality is 0 and the other end of the inequality is 0, the one that's squeezed in between should also be 0. So that is how we actually go further to prove this. Okay? So squeeze theorem allows you to set it equal to 0 as opposed to the inequality less than or equal to 0. All right? So that's about it. It's been a long lecture, but I'm glad we're done with this. And I will see you in the very last lecture, because the next one is our last section for this course. And it's really a time for jubilation. I know. So we've endured this. That's wonderful. I will see you in the next last video. Bye-bye.